We are happy to have Davide Gaiotto from Perimeter Institute for Theoretical Physics and Water Law. And the title of his talk is on the first slide, Brane quantization. Davide, please.
Right. I would like to discuss some work that I've been doing recently with Ed Witten, where we revisit his past work with Gukov on using D-branes to quantize phase spaces, and try to enrich the story a little bit to make contact more precisely with other means of quantizing things, and perhaps. I mean, the immediate motivation was for us to understand that the recent work by Frenkel, Kazhdan, and Etingof on analytic geometric Langlands in the context of Brane quantization. So, quantization, right? It's a very rich subject mathematically and physically. I'm not going to do any exhaustive discussion of the topic. I would just want to, and I will be not citing things properly, partly because I don't know the mathematics literature as well as I should on this topic. But anyway, quantization at the most naive possible level means that you have some real phase space, I'll call n to the talk, and you want to get out of it a Hilbert space. And ideally, although it's not really possible, you would like to associate to each real function on your phase space a self-adjoint operator on this Hilbert space in such a way that the commutator of these operators reproduces the Poisson bracket of the original functions. Perhaps a slightly better way to express what quantization means is to make reference to a formal path integral. If you have a real phase space equipped with a prequantum line bundle, which is a bundle whose curvature is essentially 1 over h bar times the symplectic form, then you can try to define a path integral, an integral over all possible paths from time to your phase space, or possible maps from time to your phase space, with some action, which is essentially the pullback of the connection on this line bundle. And if you could make sense of this path integral, then automatically you would get a nice Hilbert space of states, and you would get a way to describe operators associated to functions just by inserting the functions in the path integral. And the result would be sort of a topological quantum mechanics. Now, I feel really lonely when everybody turns off their cameras. Okay, but I guess if you
yeah, but mathematically you can kind of invert the logic, and since mathematically path integral is not well defined, you can try to use mathematically better defined things like deformation, quantization, in order to describe like wave functions and other things like scalar products. Yes,
right. Absolutely. I just want to say that right, all these different procedures to quantize phase space physically can be thought of as just different ways of regularizing and defining properly a path integral. And right, quantization.
That's a very naive. I mean, just because I want to understand the picture. Can you explain a little bit more what the action is in the path integral? You said it's the pullback of a Hermitian connection in this pre-quantum line bundle. It's a Hermitian line bundle, not a holomorphic one or anything.
Right. It's just a yeah. It's a smooth line bundle, right? Nothing holomorphic.
And omega is the symplectic form on your.
Yes, omega is the symplectic form, and you want the line bundle whose curvature is 1 over h bar times omega.
Yeah, that's the standard. Okay, and then what is the action in your path integral?
So you take the connection on this line bundle,
yeah,
and you pull it back. So you have a map from gamma is a map from the time, which is a real line, to your manifold. You pull it back. So you use it to pull back the connection and integrate the connection along this line.
I see. So the integrand in the second integral is basically this path in your space.
Yes.
Good.
And there is no time-dependent Hamiltonian, something like that.
That's right. This is defines what we would call the topological quantum mechanics, where the Hamiltonian is zero, so there is no time evolution. Essentially, if you're just quantizing R2 with momentum and position P and Q, this is just P the Q. PQ dot, right, is the standard.
Yes, exactly.
Path integral. And the reason you need this per-quantum line bundle is because this action has to be defined up to multiples of 2 pi I. So if you do a gauge transformation for A, it has to live in U1. Okay. Very good.
So for the benefit of those of us who don't know much of physics, so here the space M is a manifold.
Right. So
the non-bundle is it's on the manifold M, right?
Right. So M is a symplectic manifold. It's a real symplectic manifold.
Okay, I see. Okay.
And we want to associate it to Hilbert space, which roughly has a dimension which will be the symplectic volume of this phase space divided by H bar.
Okay, thank you.
And, right. So quantization is not really possible in the most beautiful sense of the term, in the sense that it's just not possible to find operators which reproduce exactly your Poisson bracket. There is not more intrinsically, it's not possible to preserve the symmetries of the classical problem. So classical, the starting point is real phase spaces with an action of symplectomorphisms and perhaps related by Lagrangian correspondences. And quantization will break these symmetries, will break these structures. So the best you can do typically is to try to say, okay, there is a bunch of symmetries I really like. I want to preserve them. I want to find a quantization which preserves those symmetries and sacrifice something else.
So again, just to understand better, these symmetries act on the Hilbert space of your theory. So if you have
so classically, symmetries are symplectomorphisms of the phase space. And now I can ask myself, okay, can I represent these symplectomorphisms as operators, unitary operators on my Hilbert space?
Yeah.
And typically the answer is no, not in a nice way.
Okay. And same for Lagrangian correspondences on M as well.
Absolutely. So again, if I have a Lagrangian correspondence between M and some M prime, I would like to get out of it an operator that goes from H to H prime.
Yeah. Okay. Okay.
Or right, and later on I'll discuss a bit more about this. So there is also the idea that if I have a Lagrangian submanifold in M, I want to get a vector in the Hilbert space. But anyway, I'll discuss it.
That was clear from the title.
Yes, in a couple of slides. And right, so something has to give. A lot has to give. There are what you physically would call anomalies. A lot of the symmetries and structures of the classical problem do not carry over, no matter how you quantize. And you need to make choices. And different choices give you equivalent quantizations. Now, this holds for the proper quantization problem. There is a simplified version of the quantization problem, which is to say, okay, I don't really try to define a Hilbert space. I just worry about the problem of defining a quantization of the algebra of functions, perturbatively in H bar. So I could try to define, at least to find what the commutators would look like in power series of H bar. And this is called deformation quantization. And even in deformation quantization, there are a lot of interesting issues and can I actually deform quantize a phase space? What happens to Lagrangians, to correspondences? What ambiguities are there? Deformation quantization is a big and very interesting subject on its own. And then on top of that, we are putting the point that we want to work with an actual H bar, which is a number, it's not a formal parameter. So on top of this, or whatever perturbative matters appear when you do deformation quantization, you have all sorts of non-perturbative issues. I mean, deformation quantization itself is quite nice and can be done in a reasonably functorial way. Although the mathematicians in the audience should tell me, should know this, should not know much better than me what to say about this. But here I want to do actual quantization. I want to get a Hilbert space at the end of the story. What are the typical ways people quantize? Well, if your phase space is a cotangent manifold, then there is a reasonably standard prescription. You take L2 normalizable half densities on the base of your cotangent bundle, and that's your Hilbert space. And then you can act on those by some differential operators. And this quantizes at least functions which are polynomial in the fiber, and generic and very generically on the base.
So can you say a little more mathematically what half densities on N are? Are they sections of some, well, are they sections of the pre-quantum line bundle maybe? Some power of that or square root?
Right, so
it's square root of the absolute value of the volume form.
That's right. So half density means that there are things whose absolute value squared can be integrated without a measure. So if I have a wave function,
so they're L2 functions basically.
That's right. Well, L2 functions, to define L2 functions, you would need a measure. L2 half densities are defined canonically.
Okay.
And you can twist them by line bundle, by one line bundle. So you can use the pre-quantum line bundle, perhaps. Now I'm getting confused.
If you need Hilbert structure, you need to multiply these two things and integrate. And so then.
That's right. To get the Hilbert. Okay. So the standard formula for the inner product Hilbert space is integral of absolute value of the wave function squared. And you can adjust the construction reasonably if your phase space is a shifted cotangent bundle, meaning that perhaps your fibers get, different patches are related by affine linear transformations instead of linear transformations. Then usually you can make things work.
Shifted not in terms of supersymmetry, but in terms of twisted.
Yeah, that's right.
It's called twisted cotangent bundle. Yeah.
Yes, that's right. Not in the sense of derived geometry, but just in the sense that, when I relate to different patches, the fiber coordinates get rotated and translated in some consistent way. And usually you can manage to quantize those by using differential operators twisted by some bundles. Anyway, the details are really not important for the discussion, and I'm not going to be able to get to the level of details of these matters. I just want to start to say that if M is a cotangent bundle or close to a cotangent bundle, there is this canonical way to quantize. And often you can encounter phase spaces which maybe they're not cotangent bundles, but which have a big open patch, which looks like a cotangent bundle. And in those situations, you can try to make things work still by just quantizing this big open patch and hoping things work on the rest. But I should stress that different ways of realizing the same manifold as a cotangent bundle will give you different answers typically. Or if you try to, take a big, to relate different patches and glue them together consistently, things might break down quantum mechanically. And so, indeed, there is a lot of very interesting math and physics that is focused just on some beautiful examples where things can be glued consistently. Think about the whole theory of cluster varieties and quantization of cluster varieties. It's all based on the fact that some symplectomorphisms can be nicely quantized. And so you can assemble the quantization of a complicated manifold as long as the patches are attached together with very specific symplectomorphisms. Now, another general strategy is to take the phase space and equip it with a complex structure so that the symplectic form is of type 1-1. And then you can define something called holomorphic quantization or Kähler quantization if it's a Kähler form, where your Hilbert space consists of holomorphic sections of some line bundle, which is now an holomorphic line bundle whose curvature is the symplectic form. So holomorphic sections roughly of the pre-quantum line bundle. And when you do that, you get to quantize at least functions which are close to being sums of products of holomorphic and functions. I think a reasonable way to think about it is you can quantize functions which are sufficiently analytic so that you can extend them to some neighborhood of M in a complexification, so that the holomorphic and anti-holomorphic coordinates can be treated as reasonably independent. But anyway, right, these are just, there's a big literature on this sort of geometric quantization strategies where you present your phase space in some special way and you get some nice enough quantization. And different presentations are typically not consistent with each other. So Brane quantization is another recipe, if you want. It's just another way to produce a quantization of a phase space. It gives results which you might or not like, which have nice features. And in some situations, you can prove that it agrees with other types of quantization. And perhaps it can be used to relate types of quantization which otherwise would look unrelated. So for example, I feel reasonably confident that a lot of those important miracles where you could quantize things patch by patch and things would work happened because secretly this was Brane quantization. For example, like the quantization of cluster varieties, so the real locus in cluster varieties is very naturally a Brane quantization. And I might be able to discuss it at the very end. Anyway, what are the ingredients that go in a Brane quantization? The first step is a bit similar to what happened for the holomorphic quantization, is to complexify your phase space. So in order to do Brane quantization, you need to be able to realize your initial phase space M as a real locus in the fixed point of some involution of a complex symplectic manifold, which I will call Y, with complex symplectic form capital omega. Now, what do I want from this Y? I will discuss it a little bit later. But the next step of the strategy is to define the so-called A-model whose target space is Y with a complexified Kähler form, complexified symplectic form capital omega. So the A-model typically depends on the data of a symplectic form, a real symplectic form, and the B field. And here we take the real symplectic form to be the imaginary part of omega, and the B field to be the real part of omega. Now, if you don't know what the A-model is, what I can say is that so if you know what the quantum field theory is, what topological quantum field theory is, I could say that the A-model is a two-dimensional topological quantum field theory attached to certain pieces of data. Another useful perspective, perhaps, is that the A-model is a factorization algebra. If you giving the model means to essentially give an E2 algebra attached to this data, together with some nice category of E1 modules called branes, which are boundary conditions for the A-model. I don't know how much of the audience have heard the term A-model before, or brane.
Yeah, I mean, people here are familiar with A-model in the context of mirror symmetry.
Right.
But
So
what you mean is something else, because you have branes which are not Lagrangian, and so with BCC in your next line. So then,
right. So indeed, so people are usually most familiar with the A-model on a Calabi-Yau manifold, and there most branes you encounter are Lagrangian submanifolds of your Calabi-Yau. Sometimes you can encounter other branes that still make sense in the A-model, although they're pretty rare. They're called coisotropic branes. And in this situation, we use one of those, which is available precisely in this setup when you have a complex symplectic manifold. And if you like to think in terms of D modules, I could say something, but I don't know if that's particularly useful.
I can give a meaning in terms of mathematically well-defined quantizations like deformation quantization, but as for the rest, I have no idea how to define it mathematically.
Right. In deformation quantization, it's reasonably straightforward. And you can understand it physically as a statement that this A model on Y is related to another topological field theory, which is a bit easier to study, which is the B model on Y. And then to go from this B model to the A model, you turn off a certain deformation, which is a Poisson bivector. And if you're familiar with the L-infinity algebras and the L-infinity algebra polyvector fields and the action on sheaves, you can probably understand this in that language. Although, as you're saying, that's just perturbative, so you will just get the deformation quantization story.
David, but before you proceed, whatever you call the Brane quantization, it will be at the physics level of rigor. Yeah. So mathematically, you can make predictions, but you cannot define what is it.
Although I can imagine that somebody can just write down and issue algebra and all of the data, a factorization algebra, and then it'll be rigorous. So I'm gonna draw pictures. These pictures,
Okay.
if you had an actual factorization algebra, this picture would make mathematical sense.
But is there a theorem that you can assign factorization algebra to a holomorphic symplectic manifold?
Well, I don't think so, but it would definitely be nice to have such a theorem. Although you'll need some conditions on this symplectic manifold, which I would like to understand better, and I will discuss them momentarily. But it's just to say that although the specific A model is perhaps not mathematically rigorous, the framework of 2D topological field theory is. And so, perhaps the pictures can still be useful and meaningful as ways to produce interesting structures. But I don't know. It's true. At the moment, Brane quantization for us is just a way to give suggestive constructions, which might be made mathematically rigorous individually, and at the same time understand. For us, it's when we look at the paper by Frenkel and others, we see a variety of mathematical constructions.
By whom?
When we look at this paper on analytic geometric Langlands by Frenkel, Kazhdan, and Etingof, there are a whole bunch of mathematical constructions in there, which we feel we should be able to understand. In order to understand them, we find the Brane quantization language helpful. Okay. So, right. So a Brane is just a boundary condition. It means it's allowed. It's something that allows me to put boundaries into the. If you're familiar with mirror symmetry, a Brane is an object in some category, which is attached to this A model. This category might sometimes be given some mathematical description in terms of the modules or Fukaya category or whatnot. From my perspective, those are all descriptions of something which underlying that exists, which is just the category of boundary conditions for the A model. Right. So when I say Brane or A Brane, you can hear object in some category attached to this data. And I'm going to use two different Branes which exist in this setup. One is what's called BCC Brane. In this setup where I turn on this B field, this is just a Brane that wraps whose support is the whole Y and has trivial Champatton bundle. So if you want, is what you get from the deformation quantization of the sheaf of the structure sheaf of Y.
It's Champatton is of rank 1.
Yes, it's the trivial
Line
one
bundle.
Champatton line bundle.
One, okay.
Yes. And normally it would be a B brane, but once you turn on the B field, it becomes an A brane. The other brane, it's supported on my real phase space. And I put on the real phase space a Champatton bundle, which is essentially the inverse of the pre-quantum line bundle. So the curvature is minus the B field.
So is it from the point of view of, I forgot whatever your symplectic form took on the complex, it's imaginary. So on the real part, it's Lagrangian or it's totally
That's
real?
right. So crucially, so capital omega was fixed by the involution. That's right. M was the fixed point of an involution of this complex symplectic manifold. The complex symplectic form is pure imaginary. Sorry, it's real on M. I'm doing a model for the imaginary part of the symplectic form. So M is a Lagrangian manifold.
Okay.
And the real part of omega, which is the B field, restricts to the symplectic form on M. And so I can make a reasonable Champatton bundle by the inverse of the pre-quantum line bundle. So these are the two actors. I call them BCC and B. Just to stress that, you know, the branes are defined by support together with the Champatton bundle. Okay, suppose that I've gotten this data, I have a definition of the model, I have a definition of these branes, then I get for free a vector space, which is the morphisms from B to BCC. As I said, these branes are objects in a category, and so I can get a space of morphisms from one to the other. And the non-trivial observation is that of Gukov-Witten is that this is actually a Hilbert space, that the holomorphic involution fixing M fixes both branes and maps and allows you to sort of map H to H dual conjugate. And so you get a nice squilinear inner product. It's not immediately obvious that this inner product is positive definite. Definitely the case when H bar is small, but I don't think there is an obvious proof that it's a Hilbert space at this point. Okay, this definition, why is this definition good or useful or interesting? Well, one of the reasons is that this space maps from B to BCC carries a natural action of endomorphisms of the BCC, right? And these endomorphisms happen to be a quantization of the algebra of holomorphic functions on Y. And so this construction gives a quantization at the very least of the functions of M, which can be complexified to functions of Y, to holomorphic functions of Y. Any questions? So this is the picture. I have this two-dimensional theory. It has boundary conditions, one I call BCC and one I call B. There is a space of states for this theory. Essentially, I take space to be a segment. I have a two-dimensional theory with space as a segment. And then I get this, associated to this, I get a Hilbert space, a space of states, which is the morphisms from B to BCC. And endomorphisms of a brane are represented by local operators that live on the boundary. And so these local operators sort of act on your space of states. And on the BCC brane, I get local operators which quantize holomorphic functions of Y. And so that deserves to be called the quantization. Although you might complain that perhaps Y is not affine, and maybe I don't have many functions, and you can try to shiftify the statement, but it's not clear that the physics is, the physical meaning of that will not be quite clear.
Even less a mathematical meaning.
Yes. And I mean, yes?
Gukov's observation is only for a home from BCC to B or BCC to any Lagrangian submanifold of the complexified variety?
So if B is not supported on a real locus, then this is not the Hilbert space.
I see.
So the Hilbert space structure comes because M is the fixed point of an involution.
Okay.
An interesting observation is that this space is also acted by, from the right, by endomorphisms of B. And so this gives you another collection of operators that act in a Hilbert space and commute with the quantization of the functions on Y. And I don't feel I understand very well the nature of these local operators. Semi-classically, they're just the endomorphisms of B are essentially the RAM cohomology of M. Not very interesting. But non-perturbatively, you might get more operators. Intuitively, I expect to get enough operators here to sort of reproduce the whole commutant of the operators on the left. So I have my Hilbert space. I managed to quantize holomorphic functions on Y. There are not many. And so there might be a lot of operators which commute with the quantization of these functions. And I expect to find those operators somehow living on B. And if you're interested in details, one can look at examples. For example, a very instructive example is to look at the quantization of R2, but as a submanifold of C star squared. And then you can get the quantum torus algebra on the BCC brane. And on the real brane, you end up finding a dual quantum torus algebra with both algebras acting at the same time on L2 normalizable functions on R. But I can, as I said, I can discuss details at the end of the talk.
Sorry, just to understand what you said in a really simple example, if I think about quantum mechanics, so my real phase space M is T star some manifold N, let's say, and you're saying the Brane cohomology of N acts on L2 functions on N?
Not on functions. Functions act on functions. The RAM cohomology should act on the cohomology.
Okay, great. So implicitly, you've already put in either some fermions or some supersymmetric quantum mechanics.
Yeah, and when I say functions, right, it's really
fine. Yeah, that's fine. You can throw in a supersymmetric version. And is the action by taking a harmonic representative and cupping, something like this?
I think so, but I should check. Okay. It's A-model, right? So to compute actions, you really need to take instanton corrections into account. So the stability is surely true at infinitesimal H bar, but and perhaps people who know deformation quantization better than me could tell me what is the center. If I deform quantize a real phase space, what's the center of the algebra usually?
Okay. No, that from the deformation quantization point of view, everything is clear except that your H bar, the Planck constant, is a parameter.
Yes, I was just trying to ask, do you happen to know what's the center? If there is a universal answer for what the center of the algebra of the form quantized algebra of functions?
Yes, what's the problem? It's an associative algebra, or if you want, indeed, as Arnav asked, you can look for a cohomology for the complex. Then, you can speak about the center just in the naive sense. Mathematically, the problem is with convergence.
Right. Is the center related to the cohomology of the phase space?
Center? No, I don't think so.
Okay, that's fine. No, that's right. Sorry, the center of the.
No,
that's right. The center of the algebra should just be the.
It's something very stupid. Like it should be very small.
Yeah.
Because be your center quasi-classically gives you symplectic leaf, and so
Yes.
If it was symplectic, then it's
No, that's right.
Yeah.
No, that's right. So this extra data of the action on B only comes when you're thinking about actual Hilbert space. I don't think the things on the right hand side would just not be visible at all in deformation quantization. They really have to do with the action of the algebra on a space of states. I mean, something that, let me say, maybe there is something I can say. Maybe not now, maybe later.
Yeah, but
Okay.
naively so far, I kind of imagine that this is a sort of deformation quantization with a Planck constant fixed, like, for example, quantum torus, which you mentioned.
Yeah, there is also Hilbert space, right? Deformation quantization gives you an algebra, and that's fine. Suppose you do deformation quantization with finite h. H is a number. This is giving you an algebra, right? I want more. I want this algebra to act as self-adjoint operators on a Hilbert space.
Then I should take Q on the unit circle, and you, which appears in the quantum torus.
No.
You can, okay.
Act on the normalizable functions of R, where I take, take the two variables to be something like e to the x and e to the p.
All right,
you get the quantum torus with Q, which is e to the 2 pi I over h bar, e to the 2 pi I h bar. Sorry, e to the I h bar.
Yes.
And there is a dual quantum torus algebra acting on the same space that commutes with the previous one, where you take something like e to the 2 pi I x over h bar.
Yeah, I understand. Yeah, it's the old construction of Faddeev something. Yeah, okay.
Absolutely.
Okay.
So, indeed, one of the beautiful examples of this is if you have y is c star times c star, and you have b to be r squared, you reproduce these constructions of where you have two dual algebras acting on the same space, and you can even use mirror symmetry to convince yourself that indeed the homomorphisms of B are a quantum torus. But I'll come back to it. Okay, so when does this work? When can I do this? Okay, so I require the existence of a Y which complexifies M. That is probably not enough. The situation where I would feel most comfortable is where Y is actually Hyper-Kähler, which means that it has this CP1 work of complex structures. It has 3 Kähler forms for 3 complex structures. Right. Y can be described as a complex symplectic manifold in a CP1 work of ways. That's because if Y is Hyper-Kähler, then I can build what I would call a physical 2-dimensional sigma model with 4,4 supersymmetry, and then twist it to get the A-model. And the physical model is something quite robust. As physicists, we feel comfortable with. Of course, it's the farthest thing from what mathematically well defined. But in any case, having the physical sigma model as a crutch gives some more confidence that the construction is solid. Also, when Y is Hyper-Kähler, it admits the sigma model admits a variety of twists, essentially one for each choice of complex structure. And both the BCC and B branes are branes of a type that we call ABA, meaning that they are A branes in the original complex structure, but they are B branes or A branes in the other two. Any questions about this? Probably a lot, but BAA or ABA branes are not exactly a common topic of discussion. But right, for example, right, this means that M if you go in one of these other complex structures, M is actually a complex manifold. So it's possible that the construction might be done when less of these holds. For example, looking at the work of Jan and Konciewicz, I would feel probably reasonably confident thinking that it can be the Brane quantization makes sense for when Y is this star of a Riemann surface. This star of a Riemann surface does not admit an Hyper-Kähler metric, but seems to be still good enough. So I would love to know what is the condition that is good enough to get a good A model for which the Brane quantization goes.
You see, we didn't pay much attention to the Hilbert space structure.
Yes.
So maybe you need Kähler forms for that. So then, but I don't know again. All right. So go ahead.
Mm-hmm.
Yeah.
Right. And sometimes the manifold Y we're interested in might have singularities and might make it look unsuitable. And in a lot of situations of interest, like geometric Langlands, cluster quantization, discussion of category O for Coulomb branches of Etingof for theories, whatever, it happens that there are some quantum field theories in dimension higher than 2, which can be used to produce this 2-dimensional theory in various ways. And so even if this 2-dimensional theory might be a bit sick looking because Y has singularities, it's sometimes possible to find a higher dimensional embedding, which is not sick, and which makes us confident the story actually makes sense. Okay. Right, and one of the basic features of this, as I was discussing, is that it automatically sort of agrees with deformation quantization of, at least for functions which are holomorphic functions on Y. And in the work with Edward, we are trying to find arguments to convince ourselves that it will agree with other standard quantizations in appropriate circumstances, like when M is a cotangent bundle or a shifted cotangent bundle, perhaps when M is a complex, one of these complex polarizations, which means that, I mean, if you can argue something like that, then perhaps even if you don't know mathematically how to define this Brane quantization, you can just refer to more standard forms of quantization, which you're comfortable with. And then the underlying Brane quantization might tell you that a variety of different quantizations must be compatible.
So can I just get a clarification on the last point, please?
Yes.
So if we go back and we're trying to geometrically quantize the real locus of the complex, so we're trying to geometrically quantize M omega, and M has a pre-quantum line bundle and everything. So
Yes.
you introduce a complex structure on it and you build a Hilbert space.
Yes.
Is that Hilbert space, well, is that Hilbert space somehow supposed to be associated with Hom B to BCC?
Well, this actually is a point we're still trying to understand. So I would suspect that if you pick the correct Kähler form, possibly yes, but is not obvious.
Okay, the Kähler form on M omega, I mean, once it's complexified.
That's right. So I'm not sure actually about that.
Mm. Well, okay, thank you. I mean, we can talk.
Okay, so next I would like to discuss the role of Lagrangian submanifold and correspondences in the quantization, in Brane quantization. So what does it mean to quantize Lagrangian manifold? From the most naive perspective, your Lagrangian manifold is defined by some equations, maybe you define it by setting to 0 some functions, and you want to find a state which is annihilated by the corresponding operators. Perhaps a slightly better perspective is that I had this path integral and trying to make sense of the path integral in a situation where the maps go from R plus to the manifold instead of from R to the manifold, so that I have a boundary at time 0. And a Lagrangian is restricting my map to lie on the Lagrangian at time 0, naively or semi-classically, seems to define a reasonable boundary condition. But when I try to define things properly, I might need to work harder. But at the end, this boundary condition at time equal to 0 will define a state. And once I have that definition, I can also hope to put sort of functions of the Lagrangian evaluated at time equal to 0, so that I should not just get one state, really. I should get a collection of states labeled by the functions on the Lagrangian manifold. Okay. So, right, from the deformation quantization point of view, as you quantize, so the algebra of functions on your phase space acts on the functions on the Lagrangian manifold just by restriction. When you quantize, you might hope that as you deform the algebra of functions, you can also deform this module to get a module for the quantized algebra of functions. Then finding a quantization of the Lagrangian means to find an image of this module inside my Hilbert space, so that the operators act on Hilbert on this image as they should. So in a sense, quantizing Lagrangians has sort of 3 steps in a perturbative perspective. First, you want to deform quantize formally in H bar. Then you can ask yourself, when does this module make sense for finite H bar? And then you need to find ways to embed this module inside your Hilbert space, which your operators are acting.
You are talking about Lagrangians in M, yeah?
Yes, these are Lagrangians.
Real Lagrangians. Okay.
Yes, real Lagrangians, absolutely. Now, in quantity, there is a natural recipe to quantize some Lagrangians. These are Lagrangians which can be complexified to a complex Lagrangian in Y. So if you have a complex Lagrangian in Y, you can define an A-brane supported on this complex Lagrangian. So you need to pick an extra data, which is a choice of flat Champerton bundle. Let me call this A-brane S because it's the brane that we're going to use to produce a state. For those who are familiar with Hyper-Kähler things, this is a brane of type BAA because it's complex Lagrangian. So it's a complex submanifold, and it's also Lagrangian for the real and imaginary part of the complex symplectic form. Now, how do I get a state or a collection of states out of a brane? Well, the first thing I would observe is that the morphisms from S to the BCC brane actually look a lot like the deformation quantization of the module attached to the Lagrangian. So this morphism from S to BCC are really a deformation of the space of holomorphic functions on the Lagrangian, or sections of the bundle. So also there is a natural map, a composition map. So if I have a map from B to S and a map from S to the BCC brane, I can compose them to get a map from B to the BCC brane. So if you give me, so I get a map that if you give me an element in here and an element in here, I can get a state in my Hilbert space. So I get for every, essentially from every element in this home B to S, I get a way to embed my module, the formation quantization module, inside my Hilbert space. Now, this is the picture associated to this. I should have probably shaded the area inside this substrip to make clear that I have a two-dimensional theory. It lives in this substrip. I have a BCC boundary condition at space 0. I have a B boundary condition at this point in space. And then at time equal to 0, I insert this boundary condition S. And to make the calculation meaningful, to produce a state, I need to also specify a local operator placed at this junction, at this corner, and a local operator placed at this corner. And the local operator between BCC and S is essentially a function of my Lagrangian up to the formation quantization. And the thing that I put in this right corner is a bit less clear. It receives important non-perturbative corrections, but roughly it should encode the possible ways of mapping this module into the Hilbert space. Any question?
It receives corrections, but if you live in if everything is exact, like in the sense of symplectic geometry, then probably there are no corrections.
Right. So, I mean, situations like I'm quantizing R2 inside T star times T star probably will have non-perturbative corrections.
Actually, maybe for C star cross C star, maybe it's opposite. You do have, but for C
yeah, no,
cross...
indeed, absolutely. So for that's a situation where I definitely will have corrections, right? So maybe this S is trying to represent the quantum dilogarithm, right? So maybe this S is defined by the equation e to the x plus e to the p equal to 1 in C star times C star.
Okay, thank you. Mm-hmm.
Anyway, in that case, what leaves there is actually a mirror symmetry that relates BCC and B, and it fixes S. So what I would find in this mysterious corner would be very similar to what I find in this corner. On the other hand, if I look at situations like R2 inside C2, then yes, probably there is not going to be any horizon non-perturbative thing here. Horizon more interesting.
Okay.
Okay, so what are the nice features of this Brane quantizational Lagrangians? A feature I particularly like appears if I look at correspondences instead of Lagrangian. So if I look at a Lagrangian correspondence between two phase spaces, which can be complexified, then in physics I get an interface, something that allows me to transform a certain 2D theory into different 2D theory. And then this gives me an operator mapping a state in this theory to a state in this theory. This operator is again described by this picture where I have sort of stretching this S interface. And to give an operator, I had to pick, again, a local something to put in here, which is a quantization of the functions of the correspondence, and something to put on the other side. Now, what I find interesting is that I can now compose correspondences. And this physically will mean literally that I take this interface S, I take this interface S prime, and I collapse them on top of each other. I was discussing in the very beginning that I don't expect the symmetries, the symplectomorphism of correspondences to the classical theory to persist after quantization. And here you can sort of identify where things go wrong in a nice way. So you can argue that the composition of interfaces at the level of just the support of the interface is fine. It's not deformed in any way. And pretty much you can argue it from the fact that they are BAA objects. But so all the subtleties, all the interesting things happen at the level of composition of corners. And so the better you understand the corners and the composition, the better you understand how to lift these correspondences quantum mechanically. If you're in a fortunate situation, maybe you can convince yourself that you have some canonical unique corners to place here, and then the composition of the interfaces will be nice.
David, and in this simplified model with deformation quantization, what does it mean?
So in deformation quantization, all the ambiguities will come from composing the corners with BCC. There is a nice example so there are nice theorems about the quantization of polynomial symplectomorphisms of Cn, of C2n.
Yeah, okay, yeah, I told you about that, yeah.
Yes, I did talk about that.
Yeah, okay, so
and that's a bit of a very nice example, because there the correspondence topologically is Cn. So it's very simple. You don't expect any complications. There is no choice of Chapleton bundle to worry about. There is a canonical corner, which is just sort of the function 1 on Cn. And this corner quite clearly composed as well. And that's sort of the Brane quantization reason for why this group of symplectomorphisms is undeformed by quantization.
Can I try to may I understand these pictures a little better, or just so both S and S prime are Lagrangian. So I want to consider self correspondences of a given phase space. So
yes, that's right.
Let's just do it self correspondences. So S and S prime are Lagrangian submanifolds of your phase space.
Yes, so Y times Y bar.
Right. Right. So in general, okay, I mean, it's just a picture, but in general, two generic Lagrangians intersect in finitely many points. So
yes,
but I get, okay, so that's okay. It doesn't matter if these S and S prime intersect as well.
No, it's a good thing.
Okay.
Actually,
It's that it doesn't happen in the picture, but obviously a picture is much simpler.
No, sorry. The picture is not depicting Y, it's depicting space-time.
Oh, it's in our, okay.
So S and S prime will do their own thing in Y, but this picture is not in Y. This picture is in space-time. So,
okay.
so I have a system where
it's difficult to see why S would give a junction between these two line operators or boundary conditions in space-time.
So let me put content in this. So I should have shaded things. I had shaded things. Somehow I must be using a, maybe I didn't save the slides after shading. So here, these are two-dimensional theories, which means in this half strip, there's a theory described by maps from the half strip into Y. And here I have another copy, another theory of maps from this half strip into Y. How can they talk together? Well, I can require the boundary value of these maps to lie in S.
Beautiful. Okay, good. Thanks.
Then if I do it here, right, I have maps on the half strip into S, into Y, then they must agree along S here.
Yeah.
Or maps here, and it must agree along S prime here.
Right. Got it. Okay.
And as you smash together S and S prime, you end up having essentially a correspondence which is just a composition of the correspondences, if you follow that.
Right. Okay. And I can maybe even think of the action of the correspondence quite explicitly now. So the correspondence is on is from Y to Y.
Yes.
And I map these two regions into Y and look at the image after the correspondence.
Yes.
Can I see what is happening to that? So S is probably preserved, the Lagrangian. But the top and bottom region are the same, or?
Sorry?
So, okay, so I take the top picture and I map it into Y, the way you said it.
Yes.
And S goes on, S is goes into a particular Lagrangian submanifold in Y. Now
yes.
I have Y with the self correspondence. And so S as a Lagrangian would still be a Lagrangian, but I mean, something non-trivial will happen. It will take Lagrangians to Lagrangians, considering correspondences are Lagrangians.
So S is a Lagrangian correspondence. And you're right, sorry. Yeah, so suppose I put a state, which is Lagrangian, I put here. Then if I bring this interface down and smash it against the boundary,
Yeah.
then this S will act on the Lagrangian just in the same way, in the usual way correspondences act on Lagrangian.
I see. Okay. So
We
I
get to affect them.
take it Lagrangian to okay.
Yes.
Thanks.
I wanted to mention a variant which occurs when my phase space was already a complex symplectic manifold. So suppose I want to quantize C2 instead of quantizing R2. And then the complexification of the complex manifold is just the complex manifold times itself. So I can embed a complex manifold Y diagonally inside Y times Y and apply the machinery of the previous slides. And after turning the crank a bit and adjusting my pictures a little bit with the doubling trick, I can find a Hilbert space, which is just a morphism from BCC to something which is sort of the conjugate of BCC. So I got a situation where I get an action of both endomorphisms of BCC and endomorphism of BCC bar commuting with each other. So I get a setup where I naturally quantized both the algebra of holomorphic functions and the algebra of antelomorphic functions, and they will commute. So, for example, if I do it if I apply this to C2, I get a Hilbert space which is the two normalizable functions on C with an action of polynomial differential operators, holomorphic differential operators, and polynomial anti-holomorphic differential operators. And a nice feature of this is that now we understand both corners. Instead of putting a real brane on the other side, I've just another version of this BCC brane. And so I just need to understand the corners between my Lagrangian and my BCC brane. And yeah, so essentially there is a canonical way to embed the deformation quantization of L and its conjugate into this Hilbert space. Okay, what time is it now? Let's see. Okay, good. I just have a couple of
go
slides.
ahead. You
So
don't.
the main example we wanted to apply this to was to understand analytic geometric Langlands, which we want to understand in terms of quantization of the Higgs of this moduli space of Higgs bundles. So imagine if you have some Riemann surface, some group, you define the space of Higgs bundles from the data, and it's a complex manifold, and I want to quantize it in this manner. And what do I get? Well, I get some Hilbert space, which is half densities. This space of Higgs bundles roughly is the cotangent bundle to Bun-G. This statement, it's better to say, and there is an open patch in the space of Higgs bundles, which look like the cotangent bundle to Bun-G. And so you can hope that the result of this brane quantization will be the space of half densities, true normalizable half densities on Bun-G. And the paper of Frenkel, Kazhdan, and Etingof is about the action of the Hitchin Hamiltonians and of certain integral operators associated to Hyper-Kähler correspondences onto this space of half densities.
Yes, so then the difference with sort of more standard picture is that your operators, they are kind of integral operators. That they are non-local. Yeah, so it's okay. Right. Yeah, there is also sort of, I believe, very old paper by Maxim. Think about it's many things, motifs and finite characteristics, where he constructed his sort of kind of generalized Langlands in a completely different direction. And I remember that he had integral Hecke operators, maybe in p-adic, kind of not over Archimedean field, but in p-adic sense. I think he will give a talk on that in a Drinfeld seminar in maybe in 10 days or so. Yeah, okay.
Right. So here there are a few. I want to say. So there are a few things that I would like to say. The first is that the two-dimensional theory whose target is the space of Higgs bundles is not terribly well defined because the space of Higgs bundles has terrible singularities. Instead, the whole picture makes sense when lifted to 4 dimensions. So there is a gauge theory, four-dimensional gauge theory, which labeled by group G, with the property that when you compactify it on a Riemann surface C, you get a two-dimensional theory whose target is the space of Higgs bundles. This four-dimensional perspective is useful in a variety of ways. For example, it helps you understand why the Hitchner-Hamiltonians and the Hecke correspondences remain commuting even after quantization. Essentially because once you lift to 4 dimensions, Hecke transformations at different locations just don't see each other. Now, one of the main ingredients in the construction of these analytic geometric Langlands is in the definition of these integral Hecke operators is a certain piece of data which we interpret as a choice of canonical corner for the Hecke operator.
So what's that? What is that? I mean, you have some interpretation of Hecke which probably make them manifest commuting or something like that. Yeah.
Right. So you need to understand why. So okay. So they get this data from some theorem of Benison and Drinfeld that there is a certain isomorphism of certain bundles which allows you to define these integral operators. Physically, this Hecke operator corresponds to some object called the 't Hooft operator. And you might ask yourself why the 't Hooft operator can end on this Brane, on this boundary condition in a particular canonical way. And we're actually still trying to understand some of these details. Now, one of the predictions of the physical picture is that there is a certain S-duality or mirror symmetry, which maps this whole picture to a different picture. This two-dimensional theory is sort of a dual description where all of these ingredients are transformed into something else without changing the answer. So when you apply S-duality, you get a theory which still has a target space, which is the moduli space of Higgs bundles. But now, what used to be this BCC Brane becomes a boundary condition called the Oper boundary condition, where essentially you want your Higgs bundles to be Opers at the boundary.
Yeah, this probably with some real mono, something like that.
Well, so this is just an Oper. So each point on the space of Higgs bundles gives you a flat connection. And here, this boundary condition is requiring the flat connection to be an Oper. This other boundary condition is requiring to be an anti-Oper. So it means that here I fix the homomorphic, I fix the bundle, and I require a certain triangular form for the connection. Here I fix the antelomorphic bundle, and require a certain triangular form for the antelomorphic connection. So the final result is that the space of states is the intersection of the Brane of Opers and the Brane of anti-Opers. there is a collection, certain collection of intersection points, each of which gives you a state. These are called real operas in the paper. At the same time, the Hecke operators on the other side become something much simpler called Wilson lines. And you can use this picture to figure out what the expectation value of a Wilson line is when acting on one of these states. And so applying as duality, you can get directly that the prediction, the big conjecture in their paper, which is that the spectrum of these Hecke operators is labeled by real operas with a very specific form for the eigenvalues, which I could explain, which is essentially one of the components of the gauge transformation, which would map the opera to the anti-opera. And you could try to draw other pictures that look like this with various modifications that come from physical constructions. You can sort of try to vary this Brane, or perhaps replace it with a real Brane. And for a lot of these ingredients, we have a physics prediction of what would happen on the other side. And so hopefully, using the physics prediction, we'll be able to get a collection of conjectures generalizing the analytic geometric Langlands conjecture of this paper by Frenkel, Kazhdan, and Etingof. So this will be, it's one motivation for this work. A final slide, which is very empty. Just to say, there are a variety of generalizations. Some of them, for example, are related to quantum, sort of an analytic version of quantum geometric Langlands, where instead of looking at the space of Higgs bundles, you try to quantize the space of flat connections, or perhaps quantize the Teichmuller locus in the space of flat connections. And you can get a nice story there again. So quantize the Hitchin section in the space of flat connections. And you can get a nice story there which can explain the general theory of quantization of the Teichmuller space, where you produce a Hilbert space where you can act with two copies of the algebra of, or the algebra of, the skein algebra on the Riemann surface. Okay. Anyway, so the Brane quantization, together with a big collection of conjecture results about this duality in Etingof 4 superior Mills, can produce a variety of interesting mathematical conjectures.
Mm-hmm.
This more or less is the punchline.
Thank you very much. And if I look for example, like Q version of Hitchin, like, periodic, like people like in this monopoles, so what will be the Hecke operators? How do they look like?
All right, so you're saying, so instead of the model expression of Higgs bundles, I could use some other interesting complex integrable, sorry, not complex integrable system, some other interesting Hyper-Kähler manifold, such as the moduli space of monopoles. Are you thinking about monopoles in periodic monopoles, doubly periodic monopoles?
Yeah, probably C star square, it's doubly periodic monopoles. Yeah.
Okay, so right, C star squared would be probably most analogous to this, I guess. Remind me, so the doubly periodic monopoles, are they cluster varieties? Yes, right? Well, not exactly.
No.
Not exactly.
Wait.
Well, the basic question is there something
But
like
yeah, I mean,
that's a nice real locus.
Yeah, but you have this, I don't know what are these reality conditions, like K2 Lagrangians, will it be okay? as examples of Lagrangians
No,
which
so
can be quantized?
So things like the Cauchy-Lagrangian condition is a condition on S. The Cauchy-Lagrangian condition presumably is a condition for the existence of this sort of corners.
Ah, all right. So then, okay. So your C star square is a complexification and
That's right. It's a
complexification of the
complexification
real yeah, okay, of the real torus, and you have S as a K2 Lagrangian, which is your interface. All right. So good, but you have all ingredients from your story, and so what will be? So what
I don't know at first sight. I mean, I could produce this by looking at five-dimensional theories, but sorry, I cannot immediately. I mean, you could try to apply also to mirror symmetries to get alternative descriptions of this of the Hilbert space and of the states. We should have to agree. Right. The first step will be to figure out what is the image of BCC under whatever dualities I want to use.
Okay,
Now,
okay, go ahead. Yeah.
I mean, someone, yeah, I don't know what exactly to say. Yeah, I don't think I can in real time find good examples based on that.
So I have a comment and a naive question. Comment is simply there are interesting. I think there are interesting Lagrangian submanifolds in modular of flat connections on a surface, which are basically given from. So if you have a three manifold whose
Yes, absolutely. Right. The flat connections is extend to flat connections on the tree manifold.
Exactly. So
Those
that
are self-mirror. So
the self-mirror. Okay.
Which in this picture, that corresponds to the fact that when I put one of those to create a state,
Yeah.
you tend to get modules which satisfies, for example, they might satisfy equations which look like the A polynomial both in AQ and in AQ tilde. Like the canonical example is the quantum logarithm, right? The quantum logarithm satisfies two different equations.
That's right.
One in the quantum torus and one in the dual quantum torus.
So okay, but
And
what? So this is only for three manifolds whose boundaries are tori or not complements.
No, I'm saying that in general, whatever module you find from the quantization of the Lagrangian, there will be image of the product of that module and its dual inside the Hilbert space.
I see.
So I have a certain Hilbert space which admits an action of two copies of the skein algebra.
Yeah. Okay.
With dual parameters, and the quantization, Brane quantization will produce naturally a module which for this product of the two copies, which look like the product of two dual modules.
Cool. I mean, it would be nice to see if one can work out invariance of the three manifold from this picture. But before that, I mean, just a really quick question. Can you elaborate a little bit more on integral Hecke operators? So the geometric Hecke operators, which were actually first defined by Narasimhan and Ramanan, which essentially modify the bundle at a point by a skyscraper sheaf at that point or by a torsion sheaf. Are these integral Hecke operators related to those in any way? I mean, it's the same modification of the underlying bundle, or it's?
Yeah, so you have wave functions which have densities on Bangee,
Yeah.
and you sort of integrate them over the fiber of your Hecke modification. It's a kind of an averaging over the Hecke modification.
I see. It's like these kernel functions. So you have an integral over the space and its product. You take a function and integrate it on this thing to get a new function on the same space. I mean, it's
Yes, right. So
integral in the sense of integration, first of all.
Sorry?
It's integral in the sense of integrating over the space.
Yes,
Not as a, okay.
that's right. It's literally an integral operator. You integrate something.
Right. Okay.
And
I mean, so such operators appear in classical story quite a lot. So Delberg studied the standard correspondences or Hecke operators on a modular curve using this kind of integral operator.
right, and the question is how to compute the spectrum of these integral
Yeah,
operators.
no, that's obviously okay. Maybe
And,
something like trace formula will work, or
and as far as I understand, it's
you need
quite
real numbers.
surprising that in the geometric setup here, you can actually give an answer to that question in terms of these real operas.
Okay. Finally, I found these formulas in Maxim's paper, which I was looking at. Indeed, he produces commuting Hecke operators, but over a local field. It's sort of local. It's okay. I'll send you the reference. So more questions?
So, Professor Soibelman, is this Koncevich's paper for Manin's birthday?
I have no idea. You see, I don't read books for a long time. It's an archive. It's called Motives, Notes on Motives and Finite Characteristics. And it's these integral formulas. I think it's in section 2.4. It's what I'm looking at. I'm not sure that I have the last version, but it's on the page 19 of that paper. And there is a Hilbert space of half densities on the projective. You know, if you have a local field, you can speak about half densities. You can speak about Hilbert space, and so he produces by explicit formulas some commuting self-adjoint operators, which are actually compact also. Yeah, okay.
Do they have any idea what the spectrum of these operators will be?
At the time he did not, but I remember I spoke to him on another occasion recently, and he told me that yeah, he was able to prove or at least argue that indeed the spectrum will be these real operators.
Oh yeah,
like they predicted. Yeah, but I don't know. I supposed to talk to him tomorrow. I can double check if you like. But he will give a talk. You know, there is this Drinfeld seminar in Chicago, and either Etingof or anyway, one of the two authors, not Kazhdan, of course, gave a talk there on their work, and in the middle of February, Maxim will probably explain what they were doing. So that's just I think on the homepage of the University of Chicago there is a schedule. I can email it to you. So then there will be history.
A quick question. So right. So with Maxim, you've done a lot of work based on holomorphic Floer theory to understand.
No. It's different. It's different. For holomorphic Floer theory, I know what's going on. But for that,
to understand when the Lagrangians can be quantized at finite h bar, have you thought at all about actually having them as states in the Hilbert space?
No, as I'm telling you, holomorphic is indeed holomorphic, which in our story with holomorphic Floer theory, we don't pay much attention to the real structure. The only thing is that in this trigonometric case, we indeed have these two opposite algebra. I mean, it's sort of this Fadeev story which you mentioned.
Doubled.
With a doubled, and we have kind of explanation in terms of Floer theory why they appear in terms of, it's called family Floer homology. But no, we didn't really want as you with Edward and with Sergei, we did not kind of try to construct the Hilbert space.
Because, for example, when you look at the star of a curve, you could try to look, have densities on the curve. And
yes, yeah.
Realize the modules that you're discussing.
Yes, kind of. If we accept that idea that it's really necessary to construct objects in the Hilbert space, yes. But what we did in your terminology, it's in the language of deformation quantization. So sort of a simplified model, which means that we had to kind of axiomatize the fact that H bar is a complex number, that it can be fixed. And then, yes, there is a question which Lagrangians, or which complex Lagrangians in our story, which of them can be quantized. And there is some theory about that.
Because in a sense, a prediction of this Brane quantization would be that, see, I could say that what you're giving me conditions for having these blue corners. And then, once you give me the condition for having a blue corner on both sides, then there should automatically be this a realization in the Hilbert space. This should be sort of the message. What you have done with Maxime should be sufficient to actually get a true quantization.
Yeah, that's possible. Actually, there is another approach to the story, which I would say uses derived language. When you do not start with functions on your complexified phase space on your Y, but you consider a category of perfect modules, like complexes of vector bundles, roughly speaking. And then you ask how to deform this category. And what we do, we also want to have some finite numbers, like volume of finite dimensional, for example, Hilbert space. In our analogy would be a compactification of your Y. And then we quantize category of perfect modules of this compactified thing, and this is part of the deformation theory. And then we look for a subcategory of objects which has Lagrangian support. Yeah, it's like for the cotangent bundle, it would be like holonomic models, and there is this deformation theory for that, and we worked it out. So then basically our tool would be to use an appropriate deformation theory for compactified Y. And kind of, then when you compactify, everything becomes finite. All extension groups, everything, it's sort of like you work, like if your cotangent space were compact, I mean, space.
Yeah, I mean, it'd be nice to sort of show that there is a unique morphism. So, this sort of picture is like working with the product of the category of the modules and the one of the bar modules, right? And it's, half densities on C are both a D module and a D bar module.
Yeah, that's one way.
And somehow you would like to say that if I take the product of one of your modules and its conjugate, there is unique, or there is a natural morphism into the half densities.
Actually, for D module, if I'm not mistaken, there is this Kashivara theorem that if you look for your manifold with an opposite complex structure, then your category of D modules is just opposite to what you had previously. So
right, which somehow is the fact that here I have a left bundle and a right
bundle.
bundle.
Yeah, that's what I mean. Yeah. But I know it for D modules, we proved it with Maxime for QD modules, like case of C star.
Right, this space of half densities has is like a module for the category times its opposite, right?
Mm-hmm.
I mean, pairing. I mean, sorry, so I have to say, right, there is something like an isomorph, an infinity morphism from the modules times the bar modules to C or whatever.
Yeah, you can.
This picture.
Yes, if you can. And actually, as for the BCC, if you work in terms like mathematically in forms of the deformation theory, and in the derived setting, not with algebras, your BCC kind of morally it's an algebra of functions on Y, quantized algebra of functions. And in the derived sense, you can choose a generator which does not have kind of to correspond to an algebra. You have more flexibility. I mean, there is a notion of a generator of category, which, and it doesn't have to be like the RAM complex of the quantized algebra. Yeah. It's very interesting.
Right. I mean, and in this paper, analytic geometric Langlands, they clearly talk a lot about the relation between the categorical and the analytic perspective on the geometric Langlands. But that should sort of be a manifestation of a more general
yeah, actually, I mean, again, kind of the one-dimensional framework which correspond to the case of curves. Like what is the Hitchin moduli space? You have a cotangent bundle and you look for coherent shifts with one-dimensional support. That's your Higgs bundles. And then you can ask how to quantize. Now you can start with an arbitrary, for example, symplectic surface, like C star square, or for example, I don't know, CP2 minus elliptic curve, or C star cross elliptic curve, and mimic the same story. Yeah. And kind of, if I understand what you said, that your kind of your Brane quantization, it just, if it's mathematically will be somehow understood, it will give a Hilbert space and
yes,
yeah. So it's more general, of course, than just geometric Langlands and conventional. I mean, whatever.
Right. And I would like to understand better the statement that somehow once you do the deformation quantization finite H bars, that should be all you need.
That's I think mathematically, I mean, it's still in its infancy. So why H bar can be fixed? you need indeed more structures. Like if you just start with what like mathematicians stupidly did many years ago, like with a symplectic manifold and want to quantize it, you cannot fix H bar. I think there were many attempts by different people, and I think Leray in 60s tried to make sense of it. But I remember I spoke to Delin maybe at 90s sometime, and he told me that probably you could not fix H bar if you would not add more structures. Just symplectic structure is not enough. And you do. So in your story you have more. You require that it's can be complexified with the property that your real thing is.
And even so, you only quantize the holomorphic functions on the complexification.
Yes, and yeah, this is BCC, but then, yeah, somehow mathematicians are certainly behind. So, so I do not, mathematically, I do not understand most of, of what is written in your slides, like what's the categories.
I find you're supposed to be an evocative talk.
Yeah, but I mean, it's nice, but I'm kind of, I know that mathematical attempts, like people try to quantize even the just what do you mean, what does it mean to quantize a symplectic manifold, which is holomorphic, UY, and it's kind of industry. Like Kashivara, Shapira, they wrote many pages, so it's not easy. Anyway. Okay, more questions, please.
Just a very highly trivial remark on Professor Soibelman's comment that they want to compactify Y. So if you're trying to geometrically quantize and the variety you're trying to quantize is compact, that makes a huge difference because holomorphic sections on a compact variety is finite.
No, it's not contact. It's Poisson. I compactify not sort of one point. I compactify by the normal crossing divisor, which means it's like you add some divisors to the surface. It's not compact.
Which feels
it's not
close
contact
to the conditions that you would require for an Hyper-Kähler matrix somehow. I don't understand the relation.
Correct, but you see, the point is that in the theory of D modules, like you have this holonomic D modules. And if you want to single out the analog of holonomic D modules, according to what we did with Maxime, you need to add some conditions at infinity, which means that you allow Lagrangians which intersect this infinity in a nice way. And so that infinity, that's the point. It's kind of, yeah.
Do you think that your compactifications might support an Hyper-Kähler metric?
This means, no, I mean, this, of course, it does not extend. Kähler metric probably, at least the symplectic form certainly has singularities at infinity.
No, of course. I mean in the complement of the singular place, but. Yeah, certainly. But it's probably better to think about that the data you provide is what's needed to make sense of the A-model. Somehow. But once you have this log decompactification that you discuss, then the A-model makes sense.
Yeah.
So I missed so when you compactify by adding normal crossing divisors, the pre-quantum line bundle, can it extend to the divisors? Probably as a
No. I'm not talking about geometric quantization
okay.
mathematically, but rather about deformation quantization.
Okay.
Because any Poisson manifold can be quantized by Kontsevich theorem in deformation quantization sense. It's over formal power series, so it's some
Yeah, that's the question I
model
wanted
for
to
what
ask you.
David explained.
Right.
Yeah.
Are there formulae for the deformation quantization of a Lagrangian? So there is this formula with the trees for the deformation.
No. I mean, all right. So no. This
formula for the module of the deformation quantization.
Okay. Now, if in some cases there is, of course, you know the formula for the wave function. If your demodule is cyclic, like if you have. Like in the cotangent bundle, if you have, say, graph of the differential or something of the function, yeah, of course, then this W, it's called WKB, perturbatively. All right. So
But
again,
Poisson case. I mean, in principle, I could imagine a proof, a construction just based on, L infinity, A infinity, and this sort of things, right? I'm putting a Poisson bivector in the bulk. I need to I probably need to turn on a Monte-Cartan element of some sort on the Lagrangian, and then compute.
Okay, yeah. So that's a good point, actually. Thank you. If we compactify this Y, as I said, and then deform like the category of perfect modules, there is an L infinity algebra which controls those deformations.
Yes.
And if I consider some Lagrangian, non-compact Lagrangian, which goes to infinity and behaves nicely at infinity, and consider all such Lagrangians and deform a subcategory of kind of sheaves supported on those. There is also L infinity algebra controlling. Yeah, so then indeed you can say that you cannot deform a particular Lagrangian and say the module, but you can deform the category of all sheaves supported on this Lagrangian, like all local. Yeah.
You cannot know, there is no way to know what's going to happen to your line bundle in a sense.
But you know that there is an object corresponding somehow hidden in this abstractly defined. Yeah. Okay.
Yeah. Understand, because you need to deform at the same time as deform the Lagrangian as you deform the bulk. And it's not canonical.
All right, so last chance to ask David a question. It's very, very interesting, but okay. Maybe 10 seconds for people to think. All right, well, thank you very much. Very, very interesting, very exciting. Yeah, okay. Thank you, David.
Nice questions. Very good.